June was Vision Research Awareness Month. One of my colleagues here at NASA Public Affairs, Brandi Dean, actually got a chance to talk to one of the doctors involved in this research taking place on board the station. She was able to actually get a personal demonstration and learn a little bit more about this research taking place on board the orbiting laboratory.
Hi, welcome to the Flight Medicine Optometry Clinic at Johnson Space Center, where in honor of Flight Research Awareness Month, we are here talking with Dr. Bob Gibson, who's one of our optometrists, and he's going to tell us a little bit about some of the research we're doing with the crew members on station to find out what might be causing the vision problems some of them have when they return from long flights in space. Thanks so much for joining us, Bob.
Glad to be here. Thank you.
So, let's see, what exactly are we looking at here?
Well, this device here is known as optical coherence tomography, which we call it OCT for short, which allows us to look at various structures in the back of the eye. As you may be aware, a significant number of our long-duration flyers have returned from space with structural changes to the eye. We're seeing swelling of the optic nerve, wrinkles to the retina and a choroid in the back of the eye, as well as farsighted shifts in their vision. And to give us a better understanding for these structural changes, we have this diagnostic tool, again known as OCT, which allows us to measure the back of the eye non-invasively using light instead of ultrasonic devices which use sound waves. We use light waves to look at the structures within the back of the eye, within the retina, within the optic nerve. And look for these structural changes and detect them much earlier than we would otherwise.
What kind of changes can you see with this? What do we look for at the back of the eye?
Well, if I can demonstrate with a model of the eye here.
Great.
Here we have the front of the eye known as the cornea, and if I show you a cross-section through the eye here, we have again the cornea, we have the internal lining of the eye known as the retina. All the nerve fiber layers in the retina come together to form the optic disc, which leads to the optic nerve, which is an extension of the brain. And what we're seeing in our crew members are wrinkles or folds to the inner lining, the retina, to the layer known as the choroid behind the retina. We're seeing folds in this region as well. And we're also seeing swelling of the retina and of the optic disc, again also known as the optic nerve.
And so this is a machine that allows you to see those things while the crew is still on orbit, right?
That is correct. It allows us to detect very subtle changes within just a few microns of change from what we measure pre-flight. So we can detect these changes much sooner and have a better way of monitoring these changes over time and giving us a better understanding for the mechanisms for these changes.
Is this something like an exam that people here on Earth would be taking normally as part of their eye exams?
It's something that's becoming a very valuable diagnostic tool, and your standard ophthalmology clinic. It's used for detecting and monitoring such diseases as glaucoma, other optic nerve diseases as well, and for looking at changes within the macula, like macular degeneration and other forms of retinal diseases.
Okay, so this should be at least familiar to some people here on the ground already.
Yeah, I would think so.
Okay, but probably the first time that we had one in space, I'm guessing. How I know we've been doing these for a little while now, so are you starting to get good results back, helpful data?
Yes, the crew's been amazing. We, with the very little training that they get, they've done an excellent job performing OCT on orbit, and we're getting some useful data. It's very limited data at this point, but we are getting some useful data showing some of the structural changes to the eye as a result of microgravity exposure.
Are you are you able to come up with any insight into exactly what's happening?
At this point, we really don't know. The data is fairly limited, although there's some theories that have been suggested, one being that the swelling of the optic nerve and these changes to the retina, as well as flattening of the back of the eye, of the globe, may be a result of elevated pressure behind the eye within the optic nerve sheath. So a localized pressure changes due to fluid shifts, which are experienced in microgravity. Also, another theory is that there may be elevated intracranial pressure within the brain that may be responsible for some of these changes. There's a condition terrestrially known as idiopathic intracranial hypertension, which has its similarities that we see in this spaceflight syndrome, yet there are some differences as well. And in that particular condition, we see swelling of the optic nerve, what we call papilledema. We see extension of the optic nerve sheath, flattening of the globe, and typically terrestrially that disease as a result of elevated intracranial pressure. So there are some similarities yet differences from that particular disease.
Okay, and I guess, does this machine help us narrow down the possibilities of what's going on, or does it just help us understand what's going on?
I think both. It's going to help us understand the structural changes that we're seeing and hopefully help us determine the mechanisms for these changes. Again, whether it be localized effects or maybe elevated intracranial pressure. But it's also a very useful clinical tool for diagnosing these changes and monitoring these changes over time.
Okay. All right. I think now we're going to get a demonstration, right?
We'll do it.
Okay, great.
All you have to do is, you're going to see a bunch of blue lights. Just focus on the flashing blue light.
Okay.
Okay, you can sit back.
All right.
Here's a video of your eye, Brandi. If you look up here close enough, you'll be able to actually see. Can you see movement in the blood vessel? Those are your blood cells coursing through the vessel. It's kind of hard to see, but if you look, you can see it. And
so I haven't been to space, obviously, so I wouldn't have anything that you probably are looking for, I'm guessing, or is there anything?
We're not actually, we're more interested in with videos looking at the what we call spontaneous venous pulsations. 80% of the population has a spontaneous venous pulsation, and you have one yourself. You have a nice pulsating central retinal vein right here. If you look real close, you can see it pulsating. Again, 80% of the population has that. That's considered normal.
Okay.
If you have a spontaneous venous pulsation, however, and all of a sudden disappears, that's not normal. That could be indicative of elevated pressure behind the eye, or even elevated pressure within the brain.
Okay. Well, thank you so much for showing us this and giving us the demonstration. It's very interesting, and I think it helps us understand a whole lot better what the crew is doing on orbit to find out more about their own eyes. So, really appreciate it. Again, this was Bob Gibson talking with us inside the Flight Medicine Optometry Clinic at the Johnson Space Center. We'll go back now to Space Station Live.